Hello Russell and anyone else keen enough to watch this video. Let's show that given the situation in this diagram here, that QP equals QA times QB. Now, I'm basically going to do this by firstly establishing some similar triangles. So firstly, the angle QAR is equal to 90 degrees because that's where the radius of the circle meets tangent. The radius meets the tangent because that line is a tangent to the circle. So that's radius tangent, which are at 90 degrees. And similarly, the angle QBS is also equal to 90 degrees. Now, let's say, just for argument's sake, that the angle here, I'm going to say that is theta. So that angle, so BQS, we're just going to say is equal to theta. That means that the angle here, QRA, is equal to 90 minus theta. So the angle QRA is equal to 90 minus theta. And obviously also the angle QSB is also equal to 90 minus theta. So now we have established, although this isn't quite what we need to do, that the triangles QBS is similar to the triangle QAR, and that is because they have an angle, an angle, and an angle. Three angles all the same. Now, we're going to do something neat here because that doesn't quite help us solve the problem. We're going to establish another triangle by drawing what we call a cotangent. And we'll call this point here M. So the line PM is a cotangent to both circles, and that means that the angle, because it's a tangent, the angle QPM is equal to 90 degrees, because that's another radius tangent. So that angle there is 90. This angle here is theta, so this angle up here must be 90 minus theta. Therefore, the angle, the angle QMP must be equal to 90 minus theta. Because, and that's just 100, I should have written this here, 180 degrees in a triangle, 180 degrees in a triangle. That's the rule we've used there, 180 degrees in a triangle. So, we now know that we have three similar triangles here because the triangle... Sorry, just had to put some charge in my pencil. So as I was saying, we've now established that this triangle QPM is similar to these other two triangles that we've established because they've all got the same angle. So the now we can say that the triangle, oops, just go back to a pen. The triangle QPM is similar to the triangle QBS is similar to the triangle QAR because they've got three angles the same. So now that we've established that those triangles are similar, we can look at we know that the ratio of the sides is going to be the same. So that means that the ratio of the bases, we've got three triangles here. This triangle here, this triangle here, and this triangle here. And the ratio of the bases is going to be equal the ratio of the hypotenuse, that's a hypotenuse there, that's a hypotenuse there, and that's another hypotenuse there, will be equal the ratio of the bases, that's a base, and that's a base, will be equal, as would the ratio of that side, and that side. We're going to use the bases, the ratio of the bases for these three triangles. So what am I talking about there when I'm talking about the ratio of bases? Well, we are saying that the ratio of QP, which is the base of that triangle, to QA, which is the base of that triangle, is going to be equal to the ratio of QB, which is the ratio for that triangle there, to QP. Then if we multiply that out, or cross multiply, we get QP squared equals QA times by QB. So what have I done there? I've basically times both sides by QP. If you want to think of it in terms of basic algebra. And then, obviously that and that cancels. And then I've times both sides also by QA, and that QA and that QA, and we get QP times QP equals QB times QA, or QP squared equals QA times QB. Voila, done.